Good morning. For our second and last day of singular theory section, it's a pleasure to introduce for our first talk this morning, Vincent Grandjean from UFC, and he will talk about normalizing the cotangent bundle of singular space.
All right. So thank you. I would like to express my gratitude to the organizer for inviting me. And also start with apologies because I might lack time to give a little bit of consistency to mathematical consistency to what the talk is about. So let's say that I have two goals in this talk. First, that to make sense of the title, because as such, it's not clear at all what I mean, but it's a short talk for once. It's a short title for once. And the second aim is, once I will have presented the problem we try to tackle, I'll try to give hints about some of the ingredients that are used to solve it. Okay, so it's a joint work with André Bellotto, who is Brazilian. He's a student of Daniel Panazzolo. Former students of Daniel Panazzolo, Edward Bestone, and Pierre Milman. So the context will be about resolution of singularities, mostly of real or complex varieties, and by varieties I mean algebraic or analytic. Okay. So we start with a variety, probably singular, and Y0 will be its singular locus. So Hironaka proved almost, 50 years ago that we can resolve the singularities of such a singular space, right? So what does it mean? It means that there is a map which has the following properties. So the map is the space X is smooth, the map is proper, surjective, and it's an isomorphism outside. It induces an isomorphism outside the singular locus Y0. And the preimage of the singular locus is nowhere dense. So that's what I mean, it's just everywhere of local codimension 1. Moreover, such resolution of singularities can be achieved asking that the map is a composition of blowings up. And blowings up where the centers are certain properties, that is, they are normal crossing with the exceptional locus, that is the preimage of the singular set of the starting variety, which itself is has a very, very rigid structure, that of simple normal crossing divisor. That is, it's a hypersurface. It has normal crossing divisors, and they are, moreover, simple. That is, all the components of this hypersurface are smooth. There is no self-intersection between the exceptional divisor has no self-intersection. And you can resolve the singularities of X0 with such properties. Okay? So, of course, this is an existence result, and we want to use such result for, let's say, application. We want really to use this. So this might not be enough. We might want to be more greedy about the properties we want on the resolution mapping sigma. So that's what I mean by how good can be sigma, of course. And the answer, well, it depends on the problem at hand. So I'm going to present what do we want to achieve in this work, and then I will give motivation for this because it is simpler to do it in this order. So that's, the next slide may be a little bit weird in regards of what just been presented. But, so that what we want to achieve is some things along those lines. So there is a conjecture which was given by Boris Yusin in 1998. And which is, well, he was mostly interested in complex projective varieties. But you can ask the same question for the category of space we are dealing with. So he's asking whether we can find a resolution of singularities of a given singular space such that what's what I call the pullback of the cotangent bundle, so the pullback of the regular section of the cotangent bundle of the initial variety, is locally generated by differential of the following type. So du alpha I for a certain number of them, and du beta j Vj for the remaining ones, where small n is the dimension of the initial singular space, and uv are local coordinates. So this is a local statement. So which means at every point you can find a neighborhood in the category you're working with. So that is either neighborhood for in the analytic case. So that's what is C omega, or an étal coordinate neighborhood in the algebraic case, in which you can find coordinates in this neighborhood, such that this guy is generated by differential of this type and this type, with the extra conditions. So the meaning of this splitting of coordinates is that locally, in this neighborhood, where you look, the exceptional divisor is the product of the U coordinates, US coordinates, right? The exponent alpha i's are they are vectors with S component with integer coefficients, and the S of them are linearly, well, I mean, they are just linearly independent, okay? And the beta j has still vectors with S components with integer component, in such a way that the family of exponent alpha I and beta j is totally ordered, but totally ordered for the total ordering, so which is just a partial order on NS. So the total ordering is, to be clear, I will say that an exponent is larger or equal to another if for each I the components are larger than the other one. Of course, this ordering doesn't give total order relation on where I am on this space. But this is what we require. This is what Usin was requiring here. And for the sake of vocabulary in the rest of the talk, coordinates of type UV like this, so that like in here, there will be local coordinates adapted to the exceptional divisor, right? So that means the first part in U will always, the product of all the U's will be a local equation at the points we are looking at of the exceptional divisor. All right, now, hang on. An interesting corollary, and that was part of the motivation of Usin's work, actually, is that, remember, I said Usin was interested in complex projective varieties. So which means that you can locally embed them very well in a complex projective space. And a complex projective space comes with a natural metric, which is the feminist study metric, right? So, as a consequence of such a requirement, this group, on this module here, if you can embed, or just locally embed, which you can always do, your singular space, so in a regular, sorry, this is M not here. So you embed it in a regular manifold, so regular would mean algebraic or analytic, with a Riemannian or Hermitian metric, which is also in the same category. Then you can pull back this metric on the result space, and of course, along the exceptional divisor, you will lose positive definiteness, because your mapping is not an isomorphism over this locus. It has singularities, the rank of this mapping along the exceptional divisor is at least n-1. Might be smaller than that. The pullback of the metric can't be at such points, cannot be a metric. Nevertheless, what you ask, what you see when you see conjecture is satisfied that at every point you can find a neighborhood such that the pullback of this metric is quasi-isometric, so in your neighborhood, to this metric here. And if the structure is real, we get rid of the conjugate on the conjugate C bars, all right? So quasi-isometric means what? Means that, that's here. So if you got a metric space U, and you have two metrics on them, all right? You have two metrics, G, H, metrics on a space U. So metrics is really what we learn in our classes. You say that they are quasi-isometric. If you can find a positive constant such that you can compare there this way. Okay? That's what quasi-isometry is. And of course, there is a local notion. You say they are locally isometric if you can find a neighborhood such that such relation is satisfied, in which case it means that the constant depends on the choice of the neighborhood. All right, so this is, and the reason of this remark will make sense with the next slide. Before this, actually, what we really would like to have in Newton's conjecture is that this map, I mean the resolution mapping, really comes from composition of admissible blowings up. So admissible blowings up are a special kind of blowings up. I mean, special, they are not very rare, but the centers are, of course, smooth, global, and they are normal crossing with the exceptional divisors. In particular, if they allow you to have simple normal crossing divisors. If you have this condition, you guarantee that. So, okay, now comes the reason of Newton's conjecture. Why did he wanted to find a resolution of singularities of the type specified? Okay. Actually, the story starts almost 15 years earlier with Xiang and Patty. Xiang and Patty. So there is a result, but the important part is Xiang and Patty, in their paper, they proved that the L2 cohomology of X0, so X0 is a normal projective surface, complex normal projective surface, is isomorphic with the intersection cohomology with middle perversity, right? So if you deal with L2 cohomology, well, you're not interested in particularly in one metric, but you have the same cohomology if you work with quasi-isometry of the given metric. If you have something which is integrable which is L2 integrable, you take a quasi-isometric metric, it will still be L2 integrable. So this requirement this remark here, but if you start with a metric which is very, very twisted after blowings up, when you lift it back, but you still have something in a simple form that you can use to make computation, this form here. And if you're interested in the L2 cohomology problem, you will have the same L2 cohomology using such form as working with this one, if you manage to patch globally in a meaningful way all these forms. So what they prove, the result which we are interested in, and which in the paper of Xiang and Patty is just merely a technical lemma. It's just a tool. They need to find a resolution of their normal surface singularity with properties of this type, and then they can compute, really. They give normal forms of metrics on the resolution surface, on the result surface, with four real variables, using the exponent, these ones and these ones. And with this, they are able to construct this isomorphism. But in their paper, this is just not even called a theorem. Just they make computation, and in the end, they say, we have the metric of this form, of this form, of this form, and that's it. And then they can use this to prove this result here. And this is one, at least. For me, that was the motivation I had when we started investigating resolution singularities with such properties. That is, how we can use, can we use resolution singularities to deal with metric problems occurring in the neighborhood of a singular set? There are other motivations. A statement like this can be used, for instance, and that's one of the motivations of André Bellotto, can be used in monomializing one forms when you are interested in singularities of foliations. You can do that. Or another motivation, which is interesting Bierstone and Millman, is also the monomization of morphism. Whether you can, when you get a morphism between two varieties, you can lift, and you can find blowings up at the source and the target, so that when you lift, you get a map between the resolved space, let's say, or the new space, which is monomial, which locally is monomial in every point, which in general is not true. This map in general is rarely monomial or even locally monomial, because it would mean that it would be locally toric, which is not the case for most singularities. Anyway, so this was about motivation, and I'm okay. So the result is the following. That's rather fresh, or so is that in dimension lower than 3, you can find a resolution of singularities which satisfies Euclidean conjecture. But be aware that unlike many results about resolution singularities, this one is really not stable. In the sense, not stable in the sense that even if you get resolution singularities, which satisfies Euclidean conjecture, and if you pick any other admissible blowing up, in general, you're going to break this property. So you have to do it again from here. And this is normal because the condition is very, very rigid, and this can't be helped. At least in dimension larger or equal than 3. Dimension 2 is stable. I'm going to explain a little bit why. Okay, so now let's start to give clues about how to do that. Well, because we're working with resolution singularities and we just have a local expression with coordinates, we're first going to transform the problem. We're going to transform the problem in a way that, which is much more meaningful to use resolution singularity. That is, we must, in the best case scenario, we must state the problems by means of ideals, right? Because what resolution singularity does actually just transform ideals in a controlled way. We know how to do that. So we start with a given resolution of singularities. Okay. Sorry. We pick one. Then, well, there is this module of logarithmic differential forms, and locally that's a module which, when we are given adapted coordinates, is generated by forms of this type. But I think anybody that is familiar with 3D visors is aware of what is a logarithmic form. There's no. So they would be locally generated by D, one equation of the exceptional divisor over the same equation, and the other coordinates, the differential of the other coordinates. And of course, we can embed the regular differential form into this logarithmic differential form, which, practically speaking, is just writing the regular form in the logarithmic basis. That's all what it is. Okay? So, thus, when we are given a local embedding of the singular space, well, we see that the pullback of the forms, the restriction of the forms over this neighborhood is the same as the pullback by the resolution mapping of the one forms of the regular manifold. Okay? So if capital N is the dimension of the embedding manifold, then sigma has components from 1 to capital N. And then to the resolution mapping, we can associate another Jacobian matrix, which would be the Jacobian matrix expressed in the logarithmic coordinates. So the log Jacobian matrix, and which is given by the UI DUIs of the component of sigmas and the DVs of the components of sigma as well. So we see that from the point of view of the relation between the determinants are very clear. The determinant of the Jacobian is just the product of the UIs times the determinant of the standard Jacobian matrix. And we can speak of logarithmic rank at a point, which is the rank of the logarithmic Jacobian matrix as well, which is the rank of the restriction of the differential of the resolution mapping to the intersection of all the components going through the point A. That's what it is. That's what we see here. All this part will be, at the point of the exceptional divisor, will be 0. So we're just left with the differentiation along the intersection of all the components of the exceptional divisor at the point. Okay? That's written here. At the exceptional point, this is 0. And to this mapping, we can associate small n, so that is dimension x0 ideals, which are the ideals of minors, for God's sake, of this matrix. And actually, these ideals, even though the construction is local, they do not depend on the embedding we take. It's a local definition, but they glue in a very nice coherent sheaf, and so they are very, very well defined. And with a little bit of more work, we can find X such that this is a locally free module as well. And these ideals, so the Fk, which are the ideals of n minus k minus of the logarithmic Jacobian matrix, are just the fitting ideals of this. So this is locally free, this is locally free, of this quotient. Right? And in the late 90s, Barden and Stern for complex normal projective surfaces, they restate, they reprove Tsiang-Paty result, so which is also using conjecture in case n equals 2. In terms of these ideals, using these ideals. Okay, you can restate, you can reformulate using conjecture in dimension 2 by means of these ideals. And actually, what? Well, okay, that's the page that is missing. All right. The statement is the following. So what we prove, there is a first proposition, which is that using conjecture, is equivalent to having all the FK, all these log-fitting ideals, which are principal and monomial in the exceptional divisor. Okay? So that's the slides that disappear in the latest version of the file. Let's hope there's, I don't remember later that there are other things that in between that have disappeared. So now Euclidean conjecture is formulated in terms of ideals. So we have a condition on dimension x0 of the singular space we want to resolve. Ideals, we need to make principal and monomial. So, well, we know that what does Hironaka's resolution of singularities is to pick an ideal and to make it principal and monomial in some exceptional divisor. That's what it does. So the problem is solved, no? Yeah, but there's still 15 minutes to talk. So that should be a hint that there might be a trick. Yeah, I'm a bad teacher, I know. All right, that would be true if we could guarantee that when I use an admissible blowing up, when I do that, so the fitting ideal of the new map is somehow some monomial times the pullback of the old fitting ideal. If that were true, then problem solved. Because at the end, if it's always like this, then we just use Hironaka's resolution, and that says this guy is going to come, principal and monomial. But, yeah, but in general, it is not so. Huh? In general, the pullback of this fitting ideal is not of this type. I mean, the new fitting ideal is not of this type. And this is to be expected, actually. I mean, what is to be expected that it should be more complicated than just that part. Because what we want to find a sequence of blowings up which at each step will control an information of the new resolution mapping. The ideals depend each time on the map. And so we want a condition on the ideals, similar ideals of the new map. So it's a condition of the map. So even if it is expressed in terms of ideal, it still stays a condition on the mapping. And that's why this thing is I mean, I would say it's unavoidable because with storic singularities this is going to work. But in general, that's the best you can do is that. If you don't add further hypotheses on the starting singularities, you're never going to have something as easy as that. All right. Well, let's see what we can do then. But there are things which are not that bad. The first thing is just the top, that is those with the fitting ideal with the maximal minors, transforms very well under blowings up. It's a monomial times the pullback of the old one. So this is always true. And now if P is a combinatorial blowing up, that is the center of the blowing up is an intersection of components of the exceptional divisor, then all the fitting ideals of the new map are just the pullback of the old fitting ideals. So these are very good properties. And because of that, somehow, in dimension 2, we find very easily a resolution singularities such that both fitting ideals, the top one and the bottom one, are principal and monomials. And because of that, again, because we are in dimension 2, if you do any further admissible blowings up, this property will be preserved. You will still have resolution singularities, which has Eucine, which satisfies Eucine conjecture. But this is because it's dimension 2. So now I have 10 minutes, I mean a little bit less than 10 minutes, to give hints about what are the ingredients in dimension 3. Yeah? So for the rest of the talk, in order to avoid introducing more notations, the singular locus is just it's just a discrete seat, so just isolated singularities, and which is the same as asking that the logarithmic rank of the A. So it's not rho, it's the resolution mapping, it is sigma. The logarithmic rank of the resolution mapping is 0. Because Y0 is just the image of the exceptional divisor. So if it had rank higher, the image would be of the same dimension. Okay, so what we can do in this case, and that's what I want actually, that's why I choose this hypothesis, because this is a condition we need, is just the pullback of the ideal of the singular locus is already principal and monomial. That we can achieve. And in this case, what we see is just so now F2 is the ideal generated by 1 minors. We are in dimension 3, huh? F2 is generated by 1 minors, is actually of the type a monomial times this guy. So we already have this one, which is monomial in principle. And we have the bottom one, so those with the maximal minors, the 3 minors, which we can assume already principal and monomial. So we have to deal with the log fitting ideal of the 2 by 2 minors. So we just have one, which we just have. That's a little bit of work to deal with. Okay, so then we can split it in the following way. So we're going to, in order to get through the result, we're going to introduce, an invariant, so something that's going to help us in the resolution process to say that we can resolve it. So the 2 by 2 minors ideal splits in a monomial ideal, which is maximal for this property, times another ideal, which vanishes in codimension 1 in the exceptional divisor. Whoa. Whoa. Because G is maximal for this property. And if this guy here is the full ring, then it means that this guy, this ideal, is already principal and monomial. So the trick is to make blowings up such that this component here, in the end of the resolution, is the full ring of the results manifold. So we introduce for each point in the manifold, so especially those in the exceptional divisor, we introduce this number, which is just the order of this ideal in this ring. And this ring is just the ideal of the exceptional divisor. So it's the sum of the reduced ideal of the components of the exceptional divisor. So this is an integral number of infinity. If it's equal to 0, if the ideal we want to improve is already monomial in principle. It is Zariski's upper semi-continuous, that is, it's locally maximal. In the neighborhood of a point, you only have smaller or equal values. And at any 3 points, that is at any, since we are in dimension 3, any corner point, it is either 0 or infinity. You have because of this structure. And I think I'm just going to, so there are three ingredients, but I'm just going to give one. I don't know how much familiar you are with the proofs of different proofs of the region of singularities. resolution of singularities, but at some points, the normal forms, local normal forms appear, you work with, and you have some ways to say that the local data that you extract from these forms, you can glue them in a well and in a global way. And it here is not going to be different. So let's take if we pick a S point of the exceptional divisor. So S point is a point of the exceptional divisor where S component intersect of the exceptional divisor, go through the point. So it's either 1, 2, or 3. And we pick a local embedding of the singular space, the original singular space at the point, at the image of the point. Okay? So we find local adapted coordinates at this point, A, and local coordinates in the embedding manifold. Then we can write the resolution mapping in this local adapted coordinate chart in this way. But there is a component of the resolution mapping that will be called the first, which is just a monomial. That we can do. And this is because the ideal of the 1-by-1 minors is already monomial. This is because of that. We can do that. And then all the other coordinates will be of that type. They will be divisible by the same monomial times terms which contain only monomials which are with exponent which are collinear to this one, and times something like this, an expression of this type, where, like I said, this term here has only monomials which are collinear to this one. This term Ti is either identically 0 or in the exceptional divisor it's vanishing only in codimension 1, at least 1. And delta is, as an exponent, is not collinear to alpha. So you can do that. So this is first condition. And you have a Weierstrass form now. Let's call it this way for the older component. So so I recall that the rho at a point is the order of this ideal in this ring, in the coordinate ring of the exceptional divisor. Right? When it is finite, you can split the v part of the coordinates, the other part of the coordinates, like this. And this term here, you can write it in the following way. Okay, so you have a spatial coordinates which is not really, there are many of them. Huh? It's not unique. So you can write it this way. And D is not anything, it's the minimal exponent of the derivative of Ti in the coordinates along the intersection of all the components of the exceptional divisor going through the point. So the dv coordinates. And when this guy is infinite, actually you can see that one of the aside is a local unit. So let's say S2. We can arrange so that the coefficient in the term d minus 1 is 0. This we can always do. And any monomial in this, so u delta here, so I recall, just in the expression of sigma I, you're going to have u delta times Ti, and on u delta times Si of the Q's, all the coordinates. So any monomial u delta in there is not collinear to alpha. Okay, and this is a result. You can achieve this with that, and well, let's say that just what we can do, with further blowings up, you can first make sure that at every point the exponent rho is always finite. We know that by definition at one point necessarily, so the smooth point of the exceptional divisor. Generically, the exponent is 0 because the ideal is just vanishing in codimension at least 1. And what we achieve here with this further blowings up is also that even on the intersection, on the smooth part of the intersection of two components of the exceptional divisor, this exponent is also 0. So we are left with a discrete set of points. I mean, we're left with curves in the smooth point part, and in the 2 points part, we are just left with points. And there's no corner, because earlier I said just the corner's row is either 0 or infinity. And I'm going to stop here, and I'll thank you for enduring my talk. Thank you.